Hello, and welcome back to the Deep Dive. I am so glad you are here with us today.
It's good to be here.
We have a really special session ahead of us. It is going to be a little bit different from what we normally do.
That's right.
Usually when we talk about computer programming or, software, we focus on the code.
Right. The text on the screen.
Exactly.
Yeah.
You look at the logic, we say, if this happens, then do that.
That is true. We usually stay high level on the software side.
Yeah.
But today, we're going deeper.
Much deeper.
We're going to stop looking at code as just magic text.
Yeah.
We're going to look underneath all of that. We're going to look at the machine itself.
You mean the physical hardware?
The silicon chips, the electricity, the actual metal inside your computer.
And I want to make a very special note for you, our listener, right at the start. We read your feedback.
We absolutely did.
We know that for many of you, English is not your first language. And you specifically asked us to use very simple English. You asked for a slow, detailed explanation.
Yeah, the feedback was really clear.
You told us that sometimes, technology podcasts, they can rush through the definitions and kind of leave you behind. And you said you want a long, deep explanation without any summarizing.
And we heard you loud and clear.
Eh.
So, here's our rule for today. We will not rush. We are going to treat this session like a classroom. I'll be the teacher, and we're going to walk through every single concept step by step.
Okay.
If we use a technical word, we will stop immediately and explain exactly what it means. We're going to take our time to make sure you can really visualize everything in your mind.
That is a promise, and I am going to hold you to that. If you say something too technical without explaining it, I'm stopping you.
It's a deal. I'm ready.
Okay. So let's start with the big picture. We are looking at a technical note about something called memory alignment. Now, alignment, that's a simple English word. It usually just means lining things up in a straight row, like lining up your shoes in a closet or cars in a parking lot.
Exactly. It seems really simple. But inside a computer, alignment is critical. It's one of those fundamental rules. If you don't line your data up correctly inside the computer's memory, well, bad things happen.
How bad?
Well, there are two scenarios. The best case, the best thing that can happen is that your computer just gets slow. Much, much slower than it should be.
And the worst case?
The worst case scenario is that the program crashes. It just stops working. It completely dies.
Okay. That is a big problem. And that's really the mystery I want to solve today. Because in my head, as a normal computer user, data is just data.
Right.
If I save a picture or a document or a number, I just want the computer to remember it. Why does the computer care where I put it? Why does moving a number, 1 inch to the right, cause the whole system to just fall apart?
That is the big question. And to answer that, we have to stop believing in magic.
Magic? What do you mean by that?
I mean, the magic of high-level programming languages. When you learn to code in something like Python or Java or JavaScript, the computer hides a lot of things from you. You type x equals 10, and poof, the number 10 just exists somewhere. You don't know where it is. You don't have to know how it got there. It feels like the number is just sort of floating in a cloud.
That's true. I really do visualize variables as little bubbles just floating in space.
That's the illusion the language gives you. But today, we're talking about systems programming.
Right.
We're looking at languages like C++ or Rust. These are the languages used to build the really heavy-duty stuff like game engines and operating systems. And in these languages, we have to reject that illusion. We have to look at the RAM.
Okay, let's start right there. RAM. RAM, random access memory. We all know we need it. If I buy a laptop, I look for 16 gigabytes or 32 gigabytes. But what is it physically? What am I looking at?
Okay, I want you to close your eyes for a second. Visualize a long, thin strip of green plastic with black chips on it.
Okay, I've seen that inside a computer.
Now, I want you to imagine a long row of mailboxes.
Mailboxes, like for getting letters.
Yes, exactly like that. But don't just imagine 10 or 20 of them. Imagine millions and millions of mailboxes, all arranged in a perfectly straight line, one after the other. It's like a road that goes on for miles and miles lined with these boxes.
Okay, I have the picture. A very long straight line of boxes.
This is what computer scientists call a one-dimensional array. It's just a line. Now, for the postman to deliver a letter, every single mailbox needs a label, right? It needs a house number.
Sure. Box number 1, box number 2, box number 3, and so on.
Exactly. In the computer, we call this the memory address. Every single box, every single one has a unique number. The very first box is address 0. The next one is address 1. The next is address 2. And this goes on for billions of boxes.
Billions. Wow. And what's inside each box?
Inside every single one of those mailboxes is exactly one byte of data.
1 byte. Okay, what's a byte?
A byte is a very, very small unit of storage. It's just enough room to store a single letter of the alphabet, like A or B, or maybe a small number, anything up to 255.
So if I have something big, like a photograph.
That photograph is made of millions of bytes, so it's going to take up millions of those mailboxes. But they're all in a neat row, box after box after box.
Okay, so the CPU, that's the central processing unit, the brain of the computer, it needs to find things in these boxes. So it uses the addresses. It says, go to mailbox number 500 and tell me what's inside.
Yes, that is the basic idea. But here's the first hurdle. The first place where people often get confused. If you look at the technical notes we're analyzing today, the addresses don't look like normal numbers. They don't look like 500.
Right. I'm looking at them now. I see these strange codes. I see things like 0x1f or 0x0xf or 0xf. What is that?
Yes, that is hexadecimal.
I see this all the time in air logs and think, it looks scary. It looks like complicated math code. Why don't they just use normal numbers? Is it just to look cool and technical?
No, it's definitely not for style. It's all about accuracy. To understand this, we have to remember what a computer actually is.
Oh, okay.
A computer runs on electricity. It doesn't have 10 fingers like you and me.
Right, we use the decimal system that's number 0 through 9 because we have 10 fingers on our hands.
Exactly. But the computer only has 2 fingers. Or, to be more accurate, it has switches. A switch can be on or it can be off.
0 or 1.
0 or 1. This is called binary.
Okay, I am with you on binary, zeros and ones. That makes sense.
Now remember I said a byte. One of our mailboxes contains data. Inside that one mailbox are 8 tiny little electrical switches. We call them bits.
So 1 byte is equal to 8 bits.
Correct. Now, imagine I tried to write down the state of those 8 switches using binary. It might look something like this: 1-100, 0-0-10.
Whoa, that is really hard to read.
It is very hard to read. It's long, it hurts your eyes, and it's incredibly easy to make a mistake. If you miss 1 0 or flip a 1, the whole number changes completely.
So what's the solution?
Well, engineers invented a shortcut. They realized a pattern. If you take just 4 bits, that's half a byte, sometimes called a nibble.
A nibble, okay.
There are exactly 16 possible combinations of zeros and ones you can make with those 4 bits.
16 combinations.
Got it. So they created a numbering system with 16 digits. We use our normal numbers, 0 through 9. But that's only 10 digits. We need 6 more.
So where do the other 6 come from?
They just use letters from the alphabet. A, B, C, D, E, and F.
So in this system, A is just a number.
Yep. A is just the number 10. B is 11, all the way up to F, which is the number 15. This system is called hexadecimal. Hex means 6, dec means 10, 16.
Okay, but why does this help us? How does it make things easier?
Because one single hex digit represents exactly 4 bits. So it lets us write that long, ugly string of binary like 1 and 1, 1, 1, 1, 1, 1 of as just 2 simple characters, FF.
Oh, I see. It's a compression.
It's a way to compress the electrical truth of the machine into something humans can read quickly and accurately. It is the most accurate way to write down the state of the computer's memory.
Okay, that helps a lot. So when I see 0x00 or 0x10 in these notes, that's just the address label on the mailbox. It's just written in the language that the computer, or I guess the hardware engineer, prefers.
Correct. And it's important because it helps us see patterns. You'll notice the computer loves the number 16. It loves the number 4. Hexadecimal makes those patterns really easy to see.
Okay. I am comfortable with the map now. I see the long line of mailboxes. I see the addresses written in hex. Now let's talk about moving the data. I assume since the CPU is the brain, it's very smart. If it needs the data in mailbox number 5, it just reaches out and grabs mailbox number 5. Simple as that, right?
You would think so. That would be perfectly logical for a human. But for a computer, that is a complete myth.
That's a myth. The CPU does not just grab the data it asks for.
It does not just grab the data it asks for. No. Let me give you a new analogy. We used mailboxes. Now, let's change the picture a little bit. Imagine you're at home cooking dinner in your kitchen. Your kitchen is the CPU.
Okay, kitchen is the CPU. Got it.
You realize you are missing one single ingredient, an apple.
Okay, I need an apple.
The grocery store is the RAM. But the grocery store is 10 miles away from your house. Now, would you get in your huge truck, drive 10 miles down the highway, walk into the store, buy one single apple, and then drive 10 miles all the way back?
No, that would be completely crazy. It's a total waste of gas, and it would be a huge waste of my time.
Exactly. It is incredibly inefficient. In the computer, the road, the highway between the CPU, your kitchen, and the RAM, the store, is called the bus.
The bus, like a vehicle.
Yes. And this bus is very wide. It can carry a lot of things at once. But the trip itself takes a long, long time. In computer terms, we call this time latency.
Latency just means delay, right?
Exactly. It's
Yeah.
delay. And to a CPU, which thinks in billionths of a second, a trip to RAM feels like an eternity. It's painfully slow.
So if the CPU made a separate trip for every single byte it needed, the computer would be, what, incredibly slow?
It would be crawling. It would be almost unusable. So the hardware engineers who designed these chips, they came up with a rule. We call it the 64-byte rule, or more formally, the cache line.
Okay, please explain this rule slowly. This seems really important.
It is the absolute foundation of our entire topic today. The rule is this. When the CPU decides it needs to go to memory, it never, ever grabs just one byte.
Never.
Never. It buys the whole shelf. The standard size for this shelf, or this chunk of data, is 64 bytes.
64 bytes. Okay.
So if your code asks for the data at address 0, the hardware says, okay, fine, but I'm not just getting address 0. I am going to grab everything from address 0 all the way up to address 63. That is 64 total bytes.
It grabs the neighbors.
It grabs all the neighbors. It takes that whole chunk, 64 mailboxes worth of data, and it brings it all back to the kitchen. It puts it in a special, super fast cupboard right next to the stove called the L1 cache. The cache is just memory that lives right inside the CPU itself.
I see. So now if my next instruction needs the data from address 1 or address 2 or address 3...
It's already in the kitchen. It's right there in the cupboard. You don't have to drive back to the store. The access is instant.
And this makes the computer fast.
Incredibly fast. This concept is called spatial locality. It's a good guess. It assumes that if you use one piece of data, you will probably need to use its neighbors very, very soon.
Okay, this sounds like a great system. It's brilliant, buying in bulk to save time. So what's the problem? You mentioned a crash earlier. Where does it all go wrong?
The problem comes when you're sloppy with how you pack your boxes. We call this the straddle penalty.
Straddle, that's an interesting word. It means standing with one leg on one side of something and the other leg on the other side, like standing over a puddle of water.
That is a perfect visualization, because you have to remember these chunks of 64 bytes are fixed. They are absolute. The hardware always grabs 0 to 63. Then the next chunk is 64 to 127. The lines are painted on the floor of the warehouse. You cannot move the lines.
The grid is permanent.
The grid is permanent. So let's imagine you have a piece of data. Let's say it's a number, and this number is 4 bytes long.
Okay, a 4-byte number.
Let's look at scenario A. This is the good scenario, the happy path. You place your number at address 60.
Address 60.
Okay, so it sits in box 60, box 61, box 62, and box 63.
Right, and the chunk ends at 63. So my number fits
Wow.
perfectly at the very end of the chunk. It's safely inside the boat.
Correct. The CPU goes to the store one time, it grabs the bag, your number is completely inside, everyone is happy, it's fast.
Okay.
Now, let's look at scenario B, the bad scenario.
Yeah.
Imagine you shift that data just a tiny bit, just 2 inches to the right. You started at address 62 instead.
Okay. Address 62, it's still 4 bytes long, so it occupies box 62. Box 63. Wait a minute.
Exactly. Where are the other 2 bytes?
Well, if the chunk, the cache line, ends at 63, then the next 2 bytes must be in box 64 and box 65.
And where do box 64 and 65 live?
They must live in the next chunk, the next cache line.
Precisely. Your small, simple 4-byte number is now split across 2 different shipments from the store. It is straddling the boundary line.
I can see why that's messy. But what does the CPU actually do? How does it handle that?
It's a complete disaster for speed. Here is the step-by-step process of what happens inside the machine.
No.
Step 1. The CPU asks for your data at address 62. The hardware fetches the first chunk from 0 to 63.
Right.
Step 2. It looks for your number inside that chunk. It sees only the first half. It's been cut off.
It's incomplete.
Right. Step 3. The hardware panics. It realizes the data is not whole. It's broken.
But what does it do?
Step 4. The CPU stalls.
Stalls. You mean it just stops?
It literally stops working, stops thinking, it freezes, it has to wait. It has to send the bus all the way back to the grocery store to get the second chunk of data from 64 to 127.
A whole second trip.
A whole second trip. Step 5. It gets the second chunk. Step 6. The CPU has to perform surgery, has to take the first half from the first trip and the second half from the second trip and stitch them together to make your number whole again.
That sounds like a ridiculous amount of extra work just because I was messy with my addresses.
It is. The result is that your throughput, that's the speed at which you can process data, is cut in half.
Right.
Literally a 50% speed reduction. Just because you didn't pay attention to the grid lines?
Wow. So alignment really just means respecting the grid.
That is the best and simplest definition I have ever heard. Respect the grid. If you respect the grid, the machine is fast. If you fight the grid, the machine will fight you back and be slow.
Okay, I understand slow. Slow is annoying, but at least it works eventually. But you promised me a crash. You said the program would die.
Yes. For normal data, for regular registers, misaligned memory is just slow. But for a specific type of technology called SIMD, it is fatal.
SIMD. Okay, that's an acronym. SIMD. We need to define this very, very clearly.
SIMD stands for single instruction, multiple data.
Single instruction, multiple data. Okay.
Here's an analogy. Imagine you're a boss at a construction site. You have 4 workers ready to work. In a normal computer program, you would tell one worker to lift one box. You'd say, hey, Bob, lift that box. That's normal processing.
Okay. One command, one action. Makes sense.
In SIMD, you have a megaphone. You stand up and you shout one command lift. And all 4 of your workers lift 4 different boxes at the exact same time.
Oh, I get it. So you get 4 times the work done with just one single shout.
Exactly. This makes map-heavy operations much, much faster. It's used everywhere in video games, graphics, scientific computing, anything with heavy calculations.
Okay, so how does it work?
To do this, the CPU uses huge storage areas. We call them registers. These special SIMD registers are 128 bits wide.
128 bits. Let me do the math here. A byte is 8 bits, so 128 divided by 8 is 16.
Correct, 16 bytes. The register can hold exactly 16 bytes of data. Now here is the rule, the hardware rule. It is not a suggestion.
The law?
The law. The instruction to load 16 bytes of data into this register is called movaps. That stands for move aligned, packed, single.
Move aligned. The A stands for aligned.
Yes. And the rule is, the starting address of your 16 bytes of data must be divisible by 16.
Divisible by 16, that sounds very, very strict.
It is incredibly strict. Think about it. If your data starts at address 0 point, is 0 divisible by 16? Yes, it works.
Okay.
If your data starts at address 16, is 16 divisible by 16? Yes, it works. If your data starts at address 32, yes, it works.
What if my data starts at address 4, or 8, or 12?
4 is not divisible by 16. It is a misaligned address.
So how does the hardware know? Does it sit there and do a complicated division math problem every time?
No. Division takes way too long. The hardware does a very, very simple electrical check. It's almost instant. It looks at the address in binary.
The zeros and ones?
Yes. For a number to be divisible by 16, the last 4 bits of its address have to be all 0. 0, 0, 0, 0.
All 4 have to be 0.
Yes. The hardware has a circuit that just checks those last 4 wires. If they are not all 0, the circuit refuses to close. The instruction is rejected.
It's refused, like a key that doesn't fit a lock.
Exactly. The electricity literally cannot flow to complete the operation.
Yeah.
The CPU throws a special kind of error called a general protection fault or a segmentation fault. The operating system steps in immediately and says this program is broken, and it kills it. Instantly.
It just disappears. Immediate crash. No warning.
Gone. Terminated. All because the address did not end in 4 zeros.
This leads us directly to a very specific example in the notes. They call it the 12-byte catastrophe. This sounds like a trap that a lot of beginners must fall into.
It is a trap. It is probably the most common mistake students make when they start doing game engine programming or any kind of low-level graphics work.
Okay, let's walk through the code example slowly. We're going to define a struct. Let's define that. A struct is just a way to group related data together.
Exactly, like a custom blueprint.
And in this case, we're making a blueprint for a 3D coordinate. So we have an X value, a Y value, and a Z value.
Right. And let's look at the size of each part. The X value is a decimal number, what we call a float. That takes up 4 bytes of space.
Okay.
The Y value is also a float, so that's another 4 bytes. And the Z value is a third float, another 4 bytes. So what is the total size of this object?
Okay, 4 plus 4 plus 4. That equals 12. So the entire object, our vec3, is 12 bytes big.
Correct. Now imagine we make an array. An array is just a list of things. Let's make a list of 2 of these vec3 objects. So we have item 1 and item 2 sitting right next to each other.
Okay. 2 12-byte items sitting next to each other in memory.
Let's be very careful about where we place them. Let's place item 1 at the very beginning of memory. Address 0.
Address 0. Let's check the rule. Is 0 divisible by 16?
Yes, it is.
So item 1 is safe. I can load it with that movaps SIMD instruction. No problem.
Perfect. Now, where does item 2 start?
Well, item 1 started at 0 and it took up 12 bytes. So item 2 must start right after it. It starts at address 12.
Address 12, or 0x0c in hexadecimal. Now, apply the rule. Is 12 divisible by 16?
No, absolutely not. 12 is smaller than 16. It's definitely not divisible.
Exactly. So what happens if you try to write a loop to process this list of objects using those fast SIMD instructions?
Uh-oh.
The first time through the loop, it tries to load item 1, It's at address 0. That's aligned. It works perfectly.
Right, the second time.
The second time through the loop, it tries to load item 2 from address 12. The hardware checks the address. It sees it's not divisible by 16.
Yeah.
Crash.
So the first one works, but the very next one kills the entire program.
Yes. This is why we call it the 12-byte catastrophe. The step size, how far we have to jump to get from one item to the next, is 12. But the hardware demands steps of 16. They just do not match up.
This makes perfect sense now. The math just doesn't line up with the hardware's rules. But this raises a question. If we have X, Y, and Z, that's 3 things. To fix this, why don't we just add a 4th thing to make the total size 16 bytes?
That is exactly the solution. We add a 4th component to our vector. We traditionally call it W.
W.
So now our structure has X, Y, Z, and W. Each one is 4 bytes. What's the total now?
4 times 4 is 16.
16 bytes.
So wait, I have to ask the obvious question. In 3D space, we only have 3 dimensions. Height, width, depth. What is W? Are we just adding garbage data? Is it just wasted space?
That is a fantastic question. Is it just padding like stuffing foam into a shipping box to make everything fit tightly?
Yeah.
Or is it actually useful? And the answer is it's both.
Both, okay.
We have 2 very important reasons for adding W. Reason A is a pure math reason, and reason B is a pure hardware reason. Let's look at the math first.
Okay. Why do we need a 4th number to do 3D math? It feels wrong.
It does feel a little strange, but it's because of something called transformation matrices.
Okay, a matrix is a grid of numbers, right?
Yes. In video games, things are constantly moving. They rotate, they get bigger and smaller, they move from one place to another. To calculate all of this movement, we use a special mathematical tool, a grid of numbers called a matrix. And for 3D graphics, this matrix is 4 numbers wide and 4 numbers tall. It is a 4x4 grid.
Okay, so the math tool itself is 4 by 4.
Right, so to multiply our 3D point, X, Y, Z, against this 4x4 grid, we need a 4th number to make the equation balance out mathematically. We need the W component.
And does W have a meaning?
It does. It has a very special meaning. If we set the W value to 1.0, the computer treats our X, Y, Z data as a position. It's like a specific dot in the room, a point in space. I am standing here.
Okay, W equals 1 means a location. What if it's not 1?
If we set W to 0.0, the computer treats the X, Y, Z data as a direction. It's like an arrow pointing north. It doesn't have a specific location. It just has a direction and a length.
Whoa, that is really interesting. So W actually acts like a switch. It tells the math formula whether this is a dot or an arrow.
Exactly. So W is not waste at all.
Yeah.
It is absolutely essential for the linear algebra that makes all 3D graphics work.
Okay, I accept the math reason. That is very cool. Now, what about the hardware reason? The notes mention something called the power of 2.
This is the critical physical reason why hardware engineers didn't just decide to build a 12-byte register. They could have, but they chose 16. And the reason is all about finding things in a list.
Finding things.
Yes. Think about how the CPU finds an item in an array, in a list. Imagine you want the 5th item in the list. The formula the CPU uses is start address of the list plus index multiplied by size of one item.
Okay, let's do that slowly. So start address plus 5 times the size.
Correct. Now let's look at scenario 1. Imagine the size of our object is 12 bytes, like our failed vec3. The CPU has to calculate 5 times 12.
5 times 12 is 60.
For a human, that's easy. For a CPU, multiplication is actually hard work. It's a very complex circuit on the chip. It takes time. We call that clock cycles. It consumes electricity and generates heat.
So multiplication is heavy lifting for the chip.
Yes. Now look at scenario 2. The size is 16 bytes. The CPU has to calculate 5 times 16.
5 times 16 is 80. Okay, that's a bigger number. Isn't that harder for the CPU to calculate?
It's a bigger number, but for a binary computer, it is infinitely easier. And the reason is because 16 is a power of 2.
A power of 2. You mean 2, 4, 8, 16, 32.
Exactly. In binary, multiplying by a power of 2 is a magic trick. You don't need to do any actual multiplication math at all. You just shift the bits to the left.
Shift to left. What does that mean?
Let me explain it with decimal numbers first, the numbers we use every day. Imagine you have the number 5. If I want to multiply 5 by 10, what do?
You just add a 0 at the end. 5 becomes 50.
Right. Did you have to do complex math in your head? Did you have to pull out a calculator?
No, not at all. I just wrote a 0. It was instant.
Exactly.
Yeah.
In our decimal system, which is base 10, multiplying by 10 is free. You just shift the digits over and add a 0. Well, computers use binary, which is base 2.
Okay.
In binary, multiplying by 2 or 4 or 8 or 16 is free. You just add zeros at the end.
So multiplying by 16 is just tacking on some zeros.
Yes. To multiply by 16, you just add 4 zeros to the end of the binary number. The computer has a special piece of hardware called a barrel shifter.
A barrel shifter.
This shifter is just a clever arrangement of wires. It takes the electricity representing the number and just moves it over by 4 spots. It happens instantly. It takes 0 clock cycles. It is completely free.
Wow. That is a huge insight. So multiplying by 16 is free, but multiplying by 12 costs the CPU time and energy.
Exactly. And that is why hardware engineers chose 16 bytes. They want the calculation of addresses to be instant. If they built a 12-byte register, the computer would have to stop and do slow multiplication every single time it wanted to find the next item in the list. That would completely destroy performance.
So let's talk about the practical solution. The notes mention explicit padding. What does that mean?
It means we don't rely on guesswork. We know we need 16 bytes for everything to work perfectly. So in the Titan engine, the software we are analyzing, they do not trust the compiler to figure this out. They do it manually, explicitly.
Yeah.
They define a new struct. They call it SIMD and it has 4 components, X, Y, Z, and W. So 4 components times 4 bytes each equals 16 bytes total.
Okay, let's check our alignment again with this new 16 byte size. Let's make a list. Item 1 starts at address 0.
The 0 divisible by 16? Yes.
Good. Item 1 is 16 bytes long. So item 2 starts right after it at address 16.
And is 16 divisible by 16?
Yes, of course. One time.
Okay, so item 3 starts at address 32. Is 32 divisible by 16?
Yes, 16 times 2 is 32. It works.
Every single one works. So simply by making our data structure bigger, by adding that we have guaranteed that every single item in our list will always land on a perfect multiple of 16, we fixed a crash, and we made the address calculations faster.
That is so counterintuitive. Usually you think smaller is faster, but in this case, bigger is faster.
Exactly. The structure of your data matters more than its raw size.
The notes also mention a specific command in the programming language Rust. It's called #reptransparent. That sounds very fancy. What does it mean in simple terms?
Okay, so Rust is a very safe language. Usually when you make a struct, Rust might add some of its own extra data behind the scenes. It might add a header that says this is a struct, or it might rearrange your fields to save space. It tries to be helpful.
But we don't want helpful here.
Exactly. When we are doing systems programming, we need total control. #reptransparent is a direct message to the compiler. It says, do not add anything. Do not change anything. I want this data structure in memory to look exactly like the raw hardware register.
So it's like telling Rust, get out of the way. Let me talk directly to the metal.
That's a perfect way to put it. It guarantees that the memory layout in the software is identical bit for bit to what the hardware requires. We call this a zero-cost abstraction. You get the safety and nice features of the Rust language, but the final result has the raw speed of assembly code.
Okay, we are getting very deep into the hardware now. Let's move to part 7 of our outline, a hardware deep dive. The notes mention different names for these SIMD technologies, SSE, AVX, AVX 512. What's the difference between them?
These are basically generations of the technology. You can think of them like different models of a car, a basic model, a sports model, and a supercar.
Okay, so what's the basic model?
First, we have SSE. That stands for Streaming SIMD Extensions.
Yeah.
This came out way back in 1999. The registers themselves are called XMM registers. They are 128 bits wide. They hold 4 decimal numbers, 4 floats. This is what we've been talking about this whole time.
And this is the standard that's on every computer.
Yes. Pretty much every laptop, every desktop, every gaming PC made in the last 15 years has SSE. It is the baseline.
Okay, so what came next? What's the sports model?
That would be AVX. It stands for Advanced Vector Extensions. These came out around 2011. The registers are called YMM registers, and they are 256 bits wide.
256, that's exactly double.
Yes, they are twice as big. They can hold 8 numbers at the same time instead of 4. So theoretically, they can do math twice as fast.
And then there's the supercar, the beast, AVX 512.
Yes. 512 bits wide. It can hold 16 numbers at once. These registers are absolutely enormous. You mostly find these in big data center servers that are crunching huge amounts of data, not usually in home computers.
Now, here's a question that confuses me. The notes call this a Russian doll architecture. If I buy a new computer that has AVX, do I have a separate chip for the old SSE instructions and a totally separate chip for the new AVX instructions?
No. This is the really clever part of the design.
Yeah.
Think of a Russian doll. You know the wooden dolls where you open one and there's a smaller one inside and another one inside that?
Yes.
The XMM register, the old 128-bit SSE register, is literally the bottom half of the YMM register, the newer 256-bit AVX register.
Well, bottom half.
They occupy the same physical space on the silicon chip. Imagine a long shelf that has 8 slots. That is the AVX register. The first 4 slots of that shelf. That is the SSE register.
Oh, So if I run an old program that uses an SSE instruction, I'm just using the first half of the big shelf.
Correct. The CPU just powers on and uses the first half. If you run a new program that uses an AZX instruction, the CPU powers up the whole shelf.
So nothing is wasted. The old hardware isn't just sitting there collecting dust.
Nothing is wasted. The old hardware is just a subset of the new hardware.
That is very efficient design. But this leads to a really big question. This is part 8 in our outline. If AVX is twice as big and potentially twice as fast, why does the Titan engine, this modern game engine we're looking at, usually stick to the older, smaller SSE? Why do they use SIMD 4 with 4 items instead of a SIMD with 8 items?
This is a really important design decision. And it's fascinating because it shows that what is technically better on paper is not always actually better in the real world. The notes gave 3 very solid reasons for this choice.
Okay, what's reason 1?
Reason 1 is compatibility.
Compatibility, you mean just making sure it runs on everyone's computer?
Exactly. AVX is available on about 95% of modern gaming PC. That sounds pretty good, right?
95% sounds great. That's an A grade.
But what about the other 5%? That still represents millions of people with slightly older computers or maybe cheaper laptops. If the Titan engine tries to run an AVX instruction on an old CPU that doesn't have those circuits built in, what happens?
But a computer doesn't know what that instruction means.
And it crashes instantly. It's an illegal instruction error. The game won't even start. Titan wants their engine to run on every computer, so they choose SSE because 100% of modern computers have it. They choose safety and reach over raw power.
Okay, that makes a lot of sense. You don't want to lock out millions of potential players. What's reason 2? The notes call it logic complexity.
This goes right back to our math. Game physics, 3D graphics, it's usually all about 3D vectors. X, Y, Z, and our friend W.
That's 4 numbers.
Right. And an SSE register holds exactly 4 numbers. It is a perfect fit, like a hand in a glove.
But AVX holds 8 numbers.
Right. So if you want to use AVX, you suddenly have a lot of empty space. You have your 4 numbers, but 8 slots to fill. To use AVX efficiently, you have to process 2 objects at the exact same time. You'd have to pack object A, X, Y, Z, W, right next to object B, X, Y, Z, W in the same register.
That sounds really hard to program.
It is very hard. You have to completely reorganize your entire engine to make sure everything is always grouped together in pairs. And what happens if you only have 1 object left to process?
You can't just process 1.
Well, you can, but you load it into the big 8-slot register, and you leave the other 4 slots completely empty.
So you're wasting 50% of the space and the power.
Exactly. You are paying for a big truck, but only filling it half full. So often, just sticking to the smaller, simpler SSE register is cleaner and more efficient for 3D math.
And finally, reason 3. This one really surprised me. The frequency penalty. And it has to do with heat.
Yes. This is a pure physics problem. Those AVX units are big. They have a huge number of transistors packed together. When you power them up fully to do that 8-wide math, they get hot. They generate a lot of heat.
And computers don't like heat.
No. Modern CPUs are very smart. They have temperature sensors all over them. If they detect that you're using heavy AVX instructions and the chip is getting too hot, they get scared of overheating and damaging themselves.
So what do?
They automatically slow themselves down. They lower the clock speed, which is measured in gigahertz. We call this throttling. So let's say your CPU normally runs at a fast 4 gigahertz. You start doing heavy AVX math. To stay cool, the CPU might drop its own speed down to 3.5 gigahertz.
Wait a minute, so my math might be going faster because I'm using AVX, but everything else in the game, the artificial intelligence, the loading from the hard drive, the input processing, suddenly gets slower.
Exactly, because the whole chip slowed down to manage the heat. So, ironically, trying to use the faster instructions can sometimes make your entire game feel slower and less responsive overall.
That is a brilliant trade-off. It really shows that you have to look at the whole system, not just one number on a spec sheet.
Precisely. Sometimes the smaller tool is actually the better tool for the job.
Okay, we are nearing the end of our session. I want to do some verification. The notes have some homework for the listener. Listener, if you're at your computer right now, you can try this.
Yes. Task 1. Check your own hardware. There is a free and very popular tool called CPU-Z. Or if you are on Linux, you can type lcpu in your terminal, open it up, and look for the box that says instructions.
Okay.
And just read the list. Do you see AVX in there? Do you see SSE 4.2? It will tell you exactly what your chip is capable of.
It's cool to actually verify what chips you have under the hood. It makes all of this feel more real.
Now, task 2. A math puzzle. Let's see if we learned the lesson about straddling. Expert, can you walk us through the straddle check one last time?
Okay, let's do it. Here's the puzzle. Imagine an object starts at memory address 0 by 30.
0 by 30. In decimal, that's 48.
Correct. The object starts at address 48, and the object itself is 32 bytes long. Okay, so the start is 48, the length is 32, so it ends at 48 plus 32 equals 80. So the object occupies all the mailboxes from address 48 all the way to address 79.
No, 48 to 80 is 33 bytes. It's 48 to 79.
Oh, right, 48 to 79. Right.
Now remember the cache line size. It is 64 bytes. So the first cache line is addresses 0 to 63. The second cache line starts at address 64. Does our object cross that line?
Let's look. The object goes from address 48 up past 63 all the way to 79. Yes, it crosses over the number 64.
Conclusion.
It straddles.
It straddles. The CPU will have to fetch 2 cache lines. It will stall. It'll be slow.
I can actually visualize that now. The object is lying across the crack between 2 big floor tiles.
That is a perfect image. And the CPU really hates picking things up from in between the cracks.
This has been an incredible journey. Let's just summarize what we learned today. We started with abstract code, these variables just floating in the air, and we ended up talking about silicon and heat and electricity and the physical grid of memory.
And that is the whole goal of systems programming. We learned that RAM isn't a cloud, it's a grid.
Right.
We learned that the CPU is efficient. It grabs 64 bytes at a time, like a train car.
And we learned that alignment just means lining up your data with the hardware's natural grid lines, those multiples of 16.
And if you line it up, it's fast. If you don't, it's slow. And if you use SIMD, being misaligned causes a fatal instant crash.
And my favorite part, we learned that making our data bigger actually made everything faster and safer, which is the big aha moment for today.
It really is.
Before we go, expert, leave us with one final thought, something to make us think.
We've talked a lot about speed today, alignment for performance, but I want you to think about this. Security.
Security, how does this relate to security?
We know that straddling a cache line makes the CPU stall. It takes a little bit longer. It's a tiny delay, maybe a few nanoseconds. Hackers are very, very smart.
Yeah.
And they have figured out how to measure that tiny delay.
What do you mean?
If a hacker can find a way to make your computer's CPU handle data that straddles a line, they can measure the time it takes using a very precise clock. They can see, oh, that operation took 5 nanoseconds longer than it should have. That must mean it crossed a cache line boundary.
And that tells them something.
By measuring these tiny delays in time, they can sometimes start to guess what the data is, or where secret keys are located in memory. This is a whole field of study called a side-channel attack. So, bad alignment isn't just about crashing your video game. In the wrong hands, it could potentially be used to steal your secrets.
Wow. Even the tiny, tiny delay of a cache miss can be used as a weapon. That is a heavy thought to end on. Thank you, expert, for this incredibly detailed and clear explanation.
Yeah.
You kept your promise, no rushing.
It's my pleasure. Learning this stuff takes time. You shouldn't rush.
And thank you, our listener, for joining us. We really hope this simple English version helped you visualize the machine. Take your time, review the notes, and we will see you in the next deep dive. Goodbye.